Well, this is lecture 13 of Basic Calculus 1. So, in the last 2 or 3 classes, we had covered the notion of continuity. So, today we will be talking about the another important concept, which is called differentiability of functions. So, the idea is really simple. There is a cyclist who covers 1 kilometer of distance say in 6 minutes. So, you want to find out what is the speed of the cyclist. That is easy. So, it is just the distance covered is 1 kilometer and the time taken is 6 minutes. So, it is 1 kilometer divided by 6 minutes, that will be the speed, that is the average speed. So, which if you want to convert to different units, say per hour, kilometer per hour. So, you write that 6 minutes as 1 divided by 10 hour. So, that it becomes 10 kilometer per hour. But see here, what is happening is we are just computing the average speed. So, it might happen that on the road where the cyclist is riding, that is having some uphills, some downhills, and his speed is affected. Sometimes it is faster, sometimes it is slower, and so on. So, finally, what we get is the average speed. So, now this differentiability concept is something like instantaneous speed. So, what is the speed of the cyclist at a given point? So, obviously, we cannot do that here. What we are doing is average speed only, but the average speed over some duration, say 6 minutes was here. So, now suppose it is not 6 minutes, but at a point we want to compute the instantaneous speed. So, what we do? We take that duration to be as small as possible, that is close to 0. So, let us say h is the time taken and the distance. How do you get the distance? Where from he has started, that is of course 0, but he might have covered some other distance before coming to that place from where we are measuring. So, let us say at that point is c. So, it is distance at c, when it was at c, some time c, instant of time, and after the duration of h. So, the distance covered is f of c plus h. Now, the distance covered from c to c plus h is f of c plus h minus f of c, that is the distance covered, and this we are going to divide by the duration, which is h here. This is how this is the average speed in the duration h, starting from instant of time c and going up to c plus h. Okay. Now, when you come off or speak about the instantaneous speed at the point c, at the time c, what do you do is take this distance covered close to 0. So, that means we would take the limiting process, limit of this ratio where f is the distance would give us the instantaneous speed. That is what the notion of differentiability is. So, let us give the definition. What we start is, suppose we have a function f defined from a subset D of R to R, and we are going not for the units now, we are forgetting the units. On the x axis you have say time, on the y axis you have the distance covered in kilometers and time is say hour, then you would get the ratio as kilometer per hour. Now, you are making it unitless. So, x axis is some number where time is measured, y axis is distance covered, and so on. So, f is that function which connects to this distance. Suppose f is a function from D to R, where D is a subset and C is an interior point of D. So, we will come to C because at instantaneous time we need a neighborhood of that. So, let us be taking interior point. So, recall that interior point means there is a neighborhood of C which is contained inside D, that is D contains some open interval of the type c minus delta to c plus delta. So, C is an interior point of D. In fact, we will not consider abstract subsets of D, we will consider just intervals. So, think of C as an interior point of the interval. Okay. So, f is defined. Now, what do? We take the ratio which is f of c plus h minus f of c divided by h, and limit h goes to 0. Since there is a neighborhood around c which is contained inside D, this limiting process makes sense. So, this limit, if this limit exists, that means it is a real number, we would say that the function f of x is differentiable at x equal to c. It is quite possible that the limit does not exist. So, we will see some examples to that effect. So, first of all, we are assuming that there is c is an interior point, and then we take the ratio, take h goes to 0. Now, this ratio is a new function of h. F of c is a number. So, f of c plus is another number, the ratio divided by h, it is a function of h. As limit h goes to 0, what is this value? So, if that value is a real number, it exists, then we say that f x is differentiable at x equal to c. And this limit we will write as f prime c and call it the derivative of f x at x equal to c. So, it is implicitly defined, that is, once the derivative exists, we say it is differentiable, and once it is differentiable, then only derivative exists. So, both the things are interconnected. That is why we pose it this way, that if the limit exists, we call that f to be differentiable, and whatever is the value of that limit, that is called f prime c, or the derivative of f x at x equal to c. So, this also there are different notations for writing the derivative. Sometimes we write like this, df by dx at x equal to c, and we take that c to the top, we say df by dx of c. It is probably better to write this way, but think of this as an abbreviation of this expression df by dx at c. Now, you see derivative of f x at any point x. Now, for one point c we have defined. So, now we vary c over all the interior points of D. Now, at all those points f x, we will write as f prime x, that is as usual, and we forget that c here, just assuming that it is as if at x. So, we will just write df by dx or f prime x, that is just a notation. So, here we should be a bit careful about this prime notation. So, prime means it is df by dx. Why? X is the independent variable of f, that is why I write dx here, and that is what prime means. So, that means suppose y is a function of x, then we would write y prime or f prime x, which we write as dy by dx. But if we consider x as a function of y, x equal to g of y, then x prime g prime y will mean that dx by dy. It is with respect to what variable we are taking. So, prime means that with respect to its independent variable. So, this notation will be very handy, we will see how. Okay. So, this is what it means when physically we go. Let us consider an example and apply this notion. Suppose f of x is x cubed minus x square plus x minus 2. The question is whether this function is differentiable at x equal to 1. So, all that we have to do is find the ratio f of x plus h. So, now that x is 1, so f of 1 plus h minus f of 1 divided by h, that is the limit we want to find out. If this limit exists, then we would say yes, it is differentiable at that, and that value of the limit is the derivative. Okay. So, let us go to work. F of 1 plus h is 1 plus h cubed minus 1 plus h square plus 1 plus h minus 2, that is f of 1 plus h, and f of 1 when x equal to 1, it is 1 cubed minus 1 square plus 1 minus 2. Now, when you expand it, say 1 plus h cubed, expand that and take away 1 cubed from there. So, 1 cubed goes, the other factor, all the other factors remain, and similarly 1 plus h square minus 1 square. So, that 1 square cancels, all the other factors remain, they always involve h, and 1 plus h similarly with minus 1 here, So, that takes away 1 and h remains, and minus 2 and minus 2 they cancel. So, it is h is always there. Now, we can cancel this h and simplify. So, that would give rise to answer will be 2. You can find it out, say 1 plus h cubed is 1 plus h square plus 3h plus h cubed, and from there you have taken away 1. So, this has gone, you have only this factor, and that gives h times 3h plus 3 plus h square. So, this h gets cancelled, you get only 3, all h go to 0 in the limit. So, you get 3 only from that minus 1 cubed. Similarly, from 1 plus h square and 1 square, you would get 1 plus 2h plus h square minus 1. So, 1 cancels, h cancels, h this becomes 0, another h is there. So, 2h h is cancelled, you get only 2. So, it is 3 minus 2 till now. 1 plus h minus 1, so h, that h gets cancelled, you get 1. So, that is 3 minus 2 plus 1, which is equal to 2. That is how we will be computing this limit. Since it is equal to 2, we would say that yes, f of x is differentiable at x equal to 1 with derivative equal to 2, f prime 1 equal to 2. So, let us consider the second example. Here the function is given as mod x. Question is it differentiable at x equal to 0? So, again we would proceed. So, let us take limit h goes to 0, 0 plus h mod minus mod 0 divided by h, which is mod h divided by h. Now, this limit we want to find out. So, mod h by h. Now, when you take the h really goes to 0, now you may think of left side limit and right side limit, that will be easier. So, when h is less than 0, but close to 0. So, mod h becomes minus h divided by h. So, it gives minus 1, left side limit is minus 1. If you take the right side limit, mod h equal to h. So, h divided by h gives you 1. So, since they are different, limit does not exist. Therefore, this is not differentiable at x equal to 0. That is what we get. Let us take the third problem. Here f of x is given as x to the power 1 by 3. Question is whether this is differentiable at x equal to 0. Again, we would take the ratio. So, ratio is f of 0 plus h to the power 1 by 3, which is h to the power 1 by 3 divided by h this way. So, that is h to the power minus 2 by 3. Again, this limit does not exist, it is in the form 1 by h, right. So, it will blow up. So, the limit does not exist. Therefore, this function is not differentiable at x equal to 0. Okay. So, let us consider this when function is defined on an interval a b. See, in our definition of differentiability, we have c at c when we are computing f prime c or finding out whether f is differentiable at c or not, c has to be an interior point of a b. Now, that means in this case c must be a point inside the open interval a b. So, there are other points in the domain of f which is a and b. What happens at these endpoints? At the endpoint a, if you take any neighborhood, say a minus delta to a plus delta, this is not contained inside the domain of definition of the function a b. Only a right neighborhood is contained inside this by making this delta small. But whatever delta you choose, the left neighborhood never is contained inside the domain. Therefore, the left side limit does not make any sense. Okay? So, only right side limit makes sense. So, what we do? At the endpoint a, we define the differentiability notion itself fresh. We say that f x is differentiable at x equal to a, the left endpoint, if only the right side limit exists. because that is only the relevant thing. So, that is what the definition says. If f is defined on a closed interval a b, at the left end point a it is differentiable if the right side limit of the ratio f of a plus h minus f a by h exists. So, here h is assumed to be positive. Similarly, at b the left side neighborhood makes sense, but the right side neighborhood is not contained inside the domain. So, we will say that the function is differentiable at x equal to b if only the left side limit exists. So, here h is negative. So, what is the meaning of h is negative here? If you write h equal to minus k, where k is positive, then the ratio gives f of b minus k minus f b divided by minus k, which is same thing as f of b minus f of b minus k divided by k, as k goes to 0 plus. So, also that way you can write the limit. So, whatever value we get from this limit, they will be taken by definition as the derivative of f at the endpoints. So, when x equal to a, we say that this right side limit is equal to f prime a, and when x equal to b, we will say that this left side limit is equal to f prime b. That is how at the endpoints we may give definition of this. We may not have to worry about this now. Of course, when time comes it will be helpful, that only on the endpoints how to use the notion of differentiability. Okay. Now, what happens? Suppose I have the function f is defined on a b to r, and at a we can write this as the right side limit, and at b it is the left side limit, which is same thing as limit k goes to 0 plus f of b minus f of b minus k divided by k, or in h also we can write the same thing. So, this way also becomes helpful because you are used to thinking h to be positive, but we should always remember that h can be both positive and negative when we take limit h goes to 0. At the end points only this 0 minus and 0 plus comes up. The same way we can define at the end when f is defined on intervals of this type. So, here the left side endpoint a, the limit should be taken right, h tends to 0 plus and so on, this ratio. Here it is left side limit at b, here again right side limit at a, and so on. So, that is how our definitions will carry over. Now, if the function is defined on a set, we would say that the function is differentiable on that set if and only if it is differentiable at each point of the set, just like our continuity idea. At a point, then generalize over all points to say that it is differentiable at that on the whole set. That is the way we are giving the fixing the terminology. So, it is differentiable means differentiable at every point. When a function is differentiable at every point of its domain, we would say that the function is just differentiable, forgetting this s. If s is a subset of that, differentiable on s is also okay, but once you say only differentiable, that means it is differentiable on its domain. Okay. So, the thing is, if f x is differentiable at every point x inside its domain, so we can write f prime x. At x equal to c, its value is f prime c. At x equal to another point d, its value is f prime d, and so on. So, f prime x becomes a new function obtained from f x. This is called the derivative of f x as a function, not only at its value. So, it is something like derivative of that evaluated at x equal to c gives f prime c. Both the things are there in the notation, though this is not our definition. Our definition is f prime c defined independently, and we give that as the value of f prime x at x equal to c. So, both the notations coincide. Okay, let us take another example. We consider again the function f x equal to mod x. For this we had already considered whether it is differentiable at x equal to 0 or not. So, domain of this function is the whole of R, right. Mod x is defined from R to R. Okay. Of course, its range is only non-negative real numbers. Negatives are also mapped to positives. Okay. So, once you ask whether this is differentiable or not, we have to really be concerned about all points, all real numbers. each real number, we have to see whether it is differentiable or not. And our experience says at 0 there is some problem, but if less than 0 or greater than 0, there can be different values, right, altogether different types of values. So, let us consider first say c is greater than 0. So, at c we want to find whether the function is differentiable or not, greater than 0, not equal to 0. So, say 0 is here somewhere c. Now, what happens? C is an interior point on the right side, forgetting this 0, right, because we define it in conditionally x equal to x if x is greater than or equal to 0 and minus x if x is less than 0. So, when x is greater than 0, we are considering the right side, even this is possible, but okay, at 0 we know. So, on the other side right interval, it is an interior point, means there is a neighborhood which is inside the set, even for 0 that is true. Okay. So, let us see at this point c is positive. Now, since limit we will be taking, we can really make our h to be smaller. So, let us restrict our h to be smaller than c by 2. So, that this c plus h, when you take f of c plus h, it will not go beyond this 0. So, only one, the first one we can really use, because c is bigger than 0 anyway. So, let us restrict that h, anyway it goes to 0. So, c plus h now is positive, it is lying to the right of 0, whether h is positive or negative, it does not matter. Then this limit of the ratio we take, c plus h mod minus c mod divided by h, will be c plus h, because it is positive, c plus h minus c by h, which is equal to 1. So, f prime c will be equal to 1. Because h is small, we can limit really to a convenient neighborhood. Now, when c is less than 0, we can again see what is happening, it is 0 and c is less than 0. So, we can limit our h to be smaller than, say, mod h by 2 again, mod c by 2. So, it will be something here, right, mod h is less than, it is not c by 2, it is the other way, h is smaller than mod c by 2, okay. You can write minus here, mod h is less than c by 2, minus c by 2. Then c plus h will remain here anyway, will be always negative. So, what happens? C plus is less than 0, whether h is positive or negative, we compute the ratio. So, c plus h becomes minus of c plus h, which is minus c minus h, and mod c becomes minus c. So, this is c gets cancelled and minus h by h, that gives you minus 1. Therefore, when c is less than 0, f prime c is negative. And already we know at x equal to 0, its left side limit is minus 1, right side limit is plus 1. So, f x is not differentiable at x equal to 0, right. But taking care of our definition of right endpoint or left endpoint, suppose you consider f to be defined on only a subset, say minus infinity to 0 closed, that is, this is our S now. On this subset we want to find whether it is differentiable or not. So, at the endpoint 0, in this interval minus infinity to 0, it is a right endpoint. So, the limit of the ratio will be taken when h remains negative, right. So, at 0 it is the left side limit, that becomes minus 1. We know for c less than 0 its limit is also minus 1. Therefore, on this f prime of any point c, where c belongs to this interval, will be equal to minus 1. Similarly, when you go to the right side limit is relevant. So, that gives you ratio limit as 1 at 0, the right side limit. So, whenever c belongs to closed 0 to infinity, it will be also equal to 1, not minus 1, but 1, right. So, different subsets, but 0 is included, here it is minus 1, here it is plus 1, that goes along with our definition of one-sided derivatives, right. Derivative is really one-sided now, because the domain is like that.